So one of the biggest applications that we are going to be working on in calculus is going to be particle motion. Calculus and particle motion go together really, really well, and it just gives you some real world context as to where derivatives kind of happen in the world. So velocity is essentially a derivative, and the reason why is velocity is the change in position over time. If you are going 60 miles an hour, then over 1 hour, you travel 60 miles, right? So it's a change in position over time. We usually use position as S of t. I have no reason why we do that, but then we use velocity as V of t. So notice right here, something that we can do is we can say, okay, well, at time A versus time t, then wherever you are, wherever S of t is, wherever S of A is, that you can take that change in position over change in time and find your like 60 miles an hour, let's just say. What this allows us to do is find instantaneous velocity versus average velocity. It's actually kind of like how your speedometer reads how quickly you are going in your car. It's calculating instantaneous velocity using little chunks of time that are so small versus average velocity, which would be like that secant line velocity, okay? So let's look at an example here. Let's say you have a lead weight that is on a spring and it's oscillating up and down. So one way that we can think about this position with time on a graph like this is, let's say it starts down here, but then the spring oscillates, right? So the position of the spring ends up oscillating back and forth like so. We can use a sine or a cosine function in order to model this. So you can just say, like, let's just say time starts here, and then that's like 1 revolution of the spring going up and down. Now, if I wanted to estimate V of 0 is the same as saying the derivative of 0. So let's kind of use a table of values, it says. So let's use from pi over 2 what would be like the velocity. So we'll say V of pi, V of call this t. We'll say this is V of t minus V of 0 over t minus 0. That's not true. Sorry. S of t minus S of 0 all over t minus 0. There we go. That's going to approximate for us. All right, so sine of pi over 2 is going to be 1 minus pi. Sine of 0 is 0 all over this. That's going to give me the reciprocal of 2 over pi. All right, let's do pi over 4. All right, well, the sine of pi over 4 is root 2 over 2 minus 0 over pi over 4 minus 0. So that's going to give me root 2 over 2 times 4 over pi, or 2 root 2 over pi. I'm going to go ahead and calculate what these values would be in decimals. So this is 0.64. And then what's 2 times the square root of 2 over pi? This is 0.90. We could do pi over 6. So sine of pi over 6 is 1/2 minus 0 over pi over 6 minus 0. So that's going to be 1/2 times 6 pi, or 3 over pi, 0.95. And as we keep getting closer and closer and closer and closer to 0 here, as we slide that in, we're actually going to find that these numbers get really, really close to 1. So again, here's our definition. The reason is v of t, or v of 0, is write this a little bit neater. V of 0 is going to be s prime of 0. So that's going to be the limit as t goes to 0, that's fine, of sine of t minus sine of 0 all over t minus 0. And in this case here, sine of 0 is 0, and this is 0. And so we're looking at the limit as t goes to 0 of sine of t over t. And this is one we did in a previous example in class, and we see that this is equal to 1. And you can see that with the table of values, but then this is also, this is kind of like almost like a trig identity of limits to kind of know. Some things I do see students try to do is they try to like cancel these t's here, and then they try to plug in 0, like just funny things. Sine of t, like sine is a composite function. It has to be sine of an angle. So you can't like cancel it out. It's not sine times t. It's sine of the angle 0 over 0. This is a special case, again, kind of one to make sure that you remember, is the limit of that as t goes to 0 is going to be 1.